Industrial steelmaking subjects raw iron to thousands of tons of crushing force to hammer it into usable commercial plates and sections. At the atomic level, the iron-carbon crystal lattice is theoretically isotropic. A perfectly grown block of steel should exhibit exactly the same mechanical strength, whether you pull it end to end, side to side, or top to bottom. But structural engineering reveals a different reality. This block diagram maps the standard crack plane orientations for a rolled steel section. The longitudinal axis follows the direction of the rolling mill, while the transverse and short transverse run vertically and across the plate. To measure the exact resistance to fracture along these distinct planes, metallurgists use Charpy V-notch testing. A standardized pendulum strikes the sample, calculating the precise kinetic energy absorbed before the steel snaps. This graph plots the impact energy absorbed by those different orientations at identical sulfur concentrations. The data shows a massive gap. The steel absorbs nearly double the kinetic energy when struck longitudinally compared to the transverse orientation. This chart confirms that the disparity persists across all operating temperatures. The top curve tracks the longitudinal tests, remaining on a high, ductile plateau, while the transverse tests flatline far below it. This gap is a permanent structural feature, not a cold weather artifact. Iron itself does not behave this way. This severe mechanical anisotropy is a structural defect engineered into the plate by processing artifacts known as non-metallic inclusions. To understand this failure, we must look inside the steel matrix at a microscopic scale. Scattered throughout the iron lattice are discontinuities, pockets of foreign chemistry. When the steel plate is placed under extreme tension, it rarely snaps cleanly. The primary mechanism of failure is a physical process called microvoid coalescence. Because the elastic modulus of the iron matrix differs from the rigid non-metallic inclusion trapped inside it, the two materials stretch at different rates under load. The matrix eventually pulls away from the inclusion entirely, nucleating an empty void in the metal. This diagram shows exactly how inclusion geometry dictates that failure. When force is applied perpendicularly to the longest axis of this green inclusion, the sharp, elongated tips act as extreme stress concentrators, ripping open a localized void in the gray matrix. This schematic maps the fracture life cycle. In panel A, under small strain, microvoids nucleate around scattered inclusions. Moving to panel B, continuous large strain forces the matrix to plastically deform. The isolated voids expand, and their stress fields interact ahead of the crack. In panel C, the bridges of solid steel tear apart, linking the cavities into a cleavage pathway that violently fractures the part. A rolled plate exhibits severe transverse weakness because it is packed with long, planar inclusions. When pulled apart, those wide geometric profiles act as internal wedges, splitting the matrix wide open. If geometry dictates the severity of the stress concentration, we have to isolate why these specific inclusions formed as highly elongated ribbons instead of harmless isolated spheres. The timeline points back one step to secondary processing, specifically the hot rolling mill, where thick slabs of steel are compressed into thin plates. At rolling temperatures, the various chemical compounds trapped inside the solid steel exhibit vastly different rheological behaviors. They respond to physical pressure in distinct ways. This chart tracks those responses. The top row shows alumina, a brittle oxide. Under the extreme pressure of the rolling mill, the solid alumina structure shatters, dispersing into a discontinuous string of microscopic dots. But the row labeled MNS reveals the specific culprit, manganese sulfide. Unlike brittle oxides, manganese sulfide is highly plastic at hot rolling temperatures. As the steel slab elongates, the small cast blob is crushed into a continuous flat line. This is a micrograph of an actual low-carbon steel sample. The dark horizontal streak is a heavily deformed manganese sulfide inclusion, stretched thin and flattened directly into the surrounding iron. When millions of these elongated ribbons align parallel to the direction of the rolling mill, they create a macrostructure known as banding, layer upon layer of built-in stress concentrators. The catastrophic structural weakness seen in transverse impact testing is literally forged into the metal when we plastically flatten soft manganese sulfide during secondary processing. Why is manganese sulfide inside the steel? We trace the material back to primary processing and the thermodynamics of the liquid melt. When raw iron ore and coke are smelted, oxygen and sulfur inevitably contaminate the liquid iron. They are inescapable chemical realities of the raw materials. This diagram shows the first correction, deoxidation. If oxygen is left unchecked, it forms gas bubbles during solidification, creating the porous, unstable, unkilled steel on the left. We intentionally kill the steel by adding elements like aluminum to trap the oxygen into solid particles. But sulfur requires a different intervention. If free sulfur remains in the liquid as it cools, it readily bonds with the iron to form iron sulfide. Iron sulfide settles along the grain boundaries of the crystalline lattice and has a dangerously low melting point. If you attempt to hot roll a slab containing iron sulfide, the grain boundaries melt under the friction, and the solid steel tears itself apart, a catastrophic failure known as hot shortness. To prevent the slab from destroying itself on the mill, metallurgists deliberately flood the liquid melt with excess manganese. Manganese outcompetes iron to bond with the sulfur, forming high melting point manganese sulfide instead. Manganese sulfide is a necessary chemical compromise. We intentionally synthesize it in a liquid phase to save the bulk hot workability of the slab, trading immediate manufacturing failure for downstream mechanical weakness. This creates a very rigid thermodynamic trap. We cannot eliminate the sulfur, and we must add manganese to survive the rolling mill, but doing so creates the soft inclusions that doom the finished plate to anisotropy. The modern engineering workaround is inclusion shape control. If we are forced to keep the inclusion inside the metal, we must alter its physical hardness to resist deformation under the rolling mill. By injecting exact trace amounts of elements like calcium, titanium, or zirconium into the melt, metallurgists force a secondary thermodynamic reaction directly inside the solidifying sulfide droplets. This microscopy compares the results. Panel A shows pure, highly plastic manganese sulfide. Panel C shows the rigid, engineered alternative containing zirconium. The EDS maps on the right prove this. The purple plot confirms a solid zirconium core is trapped inside the green manganese sulfide shell. Mechanically, these complex alloyed inclusions are significantly harder than pure manganese sulfide at extreme temperatures. When they hit the rolling mill, they refuse to elongate. This classification chart demonstrates the goal. By forcing the inclusion to remain in the type D globular column as isolated, non-deformable spheres, the steel avoids the planar stress concentrations that cause void coalescence. By manipulating the chemical melt at the atomic level, metallurgists arrest morphological elongation during secondary processing. We neutralize the internal wedges before they can form, permanently restoring equal isotropic toughness to the finished steel plate.